The paper we're diving into today is called Spin-Spin Interaction as Quantum Phase Measurement and the Mechanism of Atom Formation by David Lush.
Yeah, that's quite a title. And honestly, I feel like just the first line sets the scene for this incredibly deep re-examination of some basics from both quantum mechanics and classical electrodynamics.
Exactly. I mean, Lush is really trying to poke at what is at the heart of atomic formation. He brings up this idea that maybe we haven't really appreciated just how strong magnetic or spin-spin interactions could be under certain circumstances. Especially if, as the Dirac theory suggests, the electron always moves at the speed of light in these internal Zitterbewegung patterns.
Right, and let's maybe take a second on that. The Zitterbewegung thing, if you're not familiar, that's this idea from quantum theory that electrons aren't just sitting still. Mathematical quirk, not a real motion.
Yeah, and Lush is saying, what if that's not just a quirk, but it's something you can actually use to explain how atoms come together? He posits that these high-speed circular charge motions, when you consider their intrinsic magnetic moments, could lead to spin-spin interactions that are strong enough to rival the standard electric, or Coulomb, force between charges.
That leads to the core question in the paper, right? Which is, could these spin-spin magnetic interactions actually be the real driver behind atomic formation, instead of the classic view where it's just electric attraction holding everything together?
And that question matters because, I mean, if it's true, then our entire fundamental picture of what holds atoms together would shift, from seeing the Coulomb force as everything to acknowledging that a hidden, really strong, spin-driven force is playing a bigger role.
One thing that caught me is how Lush argues that this interaction doesn't always appear. It actually depends on having particles with equal mass and spins that are aligned. So, like, two electrons with the same spin orientation could attract magnetically with a force similar in strength to the regular electric force, but if their spins are anti-aligned, this force averages out.
Mm-hmm. It's very selective, this coupling. And of course, that fits, in a weird way, with quantum statistics and why some atomic configurations are stable and some aren't. But Lush doesn't stop there. He speculates that quarks and leptons, so the really fundamental building blocks, might themselves be made from more fundamental spin half particles. Which, to be honest, is kinda wild, since it revives these ideas about substructure inside elementary particles.
I think that's what's kind of both exciting and daunting about this paper. It's not just proposing a tweak, it's basically saying, hey, you know the electron? What if that's not fundamental? What if it's made of three even tinier things, with their own spins and internal dances?
Yeah, and even photons might have structure, as Lush brings in. That, by the way, is something de Broglie and others mused on decades ago, but never really became standard.
So, in terms of method, much of what Lush does is take the classical electrodynamics we know and push it into this high-speed, almost always at light speed regime, and then calculates what the electromagnetic fields would do if these zitter motions were real. He then compares these magnetic force modulations to the de Broglie matter wave, so the oscillation of these internal phases of the electron matches the famously mysterious wave function phase in quantum mechanics.
Precisely. And he argues that this quantum phase might not be some abstract mathematical thing, but actually a real physical phase between two zitter motions. So interaction between electrons becomes a measurement of their phase difference. That's a neat way to reinterpret, say, why quantum interference happens.
It's pretty wild. It reminds me a bit of, this is such a tangent, but I remember hearing about how oil droplets on vibrating surfaces can sometimes mimic quantum interference effects.
Oh, right, those bouncing droplet experiments. Basically, a classical system somehow showing quantum-like results. That's a fun analogy, even if the scale and context are so different.
Anyway, coming back, Lush even suggests that this could help explain the so-called spin-orbit coupling anomaly in atomic physics. Normally, we say there's a weird factor of two discrepancy that's only fixed by some clever relativity tricks. But here, he says if photon energy is recalibrated, the problem might resolve itself much more naturally.
It's worth saying, though, Lush recognizes the big caveats.
Welcome back to In Depth with Academia. I'm Richard Price, CEO of Academia EDU, and today I'm talking about a paper by David Lush called Quantum Wave Mechanics as the Magnetic Interaction of Dirac Particles. Woo, what a title, right? But don't worry, I'm going to break it down so it actually makes sense and, more importantly, relate it to you, the listener. And just a quick reminder, my job here is to summarize and discuss the research neutrally. I'm not endorsing any particular view or result I present. I'm just here to pull apart the ideas and lay them out, conversationally, quirks and all. Right? So, let's start with the big question the paper tackles. What's the core problem here? That central quantum mechanics is full of mysteries, but one especially weird part is why quantum particles, like electrons, seem to behave as both particles and waves. If you've heard of the famous double slit experiment, you know what I mean. Why do we have to have this weird wave function thing, sort of a probability field, governing how these particles act? Could that actually arise maybe from something more classical, like electromagnetic interactions between spinning charges? That's the bold idea at the heart of this paper. Why is this important? Well, if there's a way to reconstruct quantum behavior from something a little more down to earth, from like just charges whizzing around and interacting electromagnetically, it could change how we understand the bridge between quantum physics and classical physics. It doesn't mean quantum mechanics is wrong, but it suggests that maybe what looks strange could have a classical underpinning. That's a fascinating possibility, right? All right, let's dig a bit deeper. The paper by David Lush builds on the idea that elementary particles, like electrons, might be modeled as little point charges moving in tight, really fast circles. This involves something called Zitterbewegung, a jittery, ultra-fast motion predicted by the Dirac equation for electrons. Here, the internal circular motion, at nearly the speed of light, no less, gives the particle its spin. Now, what the author does is he looks at how two such Dirac particles would interact, not just electrically, but magnetically. And the key result, if you consider the magnetic force between these rapidly circulating charges, and here's the twist, you allow for time-symmetric electromagnetic interactions, meaning you let the future as well as the past influence the force. You get a force that isn't just static or simple. Instead, it's modulated. It oscillates in a way that mathematically resembles the quantum wave function. Let me pause for a second. That's a weird notion. Time-symmetric forces. Isn't causality important? Well, in certain formulations, like the Wheeler-Feynman absorber theory, it's legit to consider both advanced and retarded waves. Basically, you include influence running both forwards and backwards in time, which is definitely not something your high school physics teacher covered. Getting back on track, Lush finds that under these assumptions, the modulation of the magnetic force between these zeta particles solves an equation that's almost the same as the Schrödinger equation, the central equation of quantum mechanics. There's a catch, though. When you work through standard relativity, it's not an exact match. There's a factor of 2 difference. But if you use a modified version of the relativity energy formula, as some alternative theories suggest, the modulation fits the regular Schrödinger equation exactly. What does this mean for you? Well, for one, it challenges the notion that all quantum weirdness is irreducibly random or disconnected from classical physics, and more practically, it suggests that quantum wave functions might, in some sense, arise from the underlying electromagnetic dance of matter's tiniest parts. If you're studying physics or just love science, this is one way to see wave functions as representing actual patterns in the story of moving charges, not just mathematical abstractions. Quick digression, this reminds me of how sometimes if you stare at a ceiling fan spinning really fast and a light flickers at just the right speed, it looks like the fan is standing still or even spinning backwards. Your brain thinks it's seeing something real, but it's just an artifact of overlapping patterns. Is quantum weirdness like that? Patterns that emerge from complicated underlying cycles? I don't know, but it's an interesting visual. So, zooming out, the methods in the paper are, honestly, pretty technical. modeling charges as spinning at the speed of light, using equations from both classical electromagnetism and quantum mechanics, and doing some non-trivial math to link force modulations to equations like Schrödinger's. But the upshot is a set of equations showing the weirdness of quantum mechanics might map, under the right lens, onto plain old magnetic interactions between spinning charges. Of course, there are limitations. This approach so far works best for particles with the same mass and aligned spin, and it's definitely not the last word on quantum theory. The author notes that this is a starting point, and again, I am just describing a perspective, not endorsing it. Science thrives on these creative attempts to see familiar things in a new light. So, there you go. If you've ever wondered whether quantum mechanics could emerge from deeper classical processes, this paper is one attempt at that explanation. What matters for you is to remember, scientific papers aren't pronouncements of truth, but invitations to ask, could this picture be meaningful? Could it explain something I see in experiments? That curiosity is at the heart of science. Thanks for listening to In Depth with Academia. I've been Richard Price, and as always, keep questioning, keep exploring, and above all, stay curious. Let's meet again soon. Who knows what other surprising connections we'll discover. With Academia, I'm Richard Price, CEO of academia.edu, and, well, today we're really diving into something wild. We've got a paper by David Lush, and let me just say it's called On Einstein-Minkowski-Osiak Relativity, and oof, it's a doozy. Just a quick note before we start, I'll be presenting the paper's ideas neutrally. I'm not endorsing them or taking sides here, so keep that in mind. Academic research is always an exploration, not some kind of ultimate truth or finished story, right? All right, so what's this paper actually about? The core question is all about energy and relativity, and whether the way we currently calculate things like rest energy and kinetic energy in particle physics might actually be off the mark. The author builds on ideas from a guy named Osiak, and he asks, what if instead of the famous E y mc squared that's like plastered all over science textbooks, the true formula for rest energy is actually E mc squared divided by 2. That is E mc22 ho, right? If you remember your high school physics, or even if you don't, you probably know that E mc2 feels like one of those ironclad laws of the universe. But David's saying, well, maybe not. And here's why this matters. If those alternate formulas are right, then, well, the universe might not actually conserve energy in the way we expect, especially in high-speed or relativistic collisions between particles. That's huge because energy conservation is like one of the most sacred cows in science. Take that away, and wow, everything feels up for grabs. Also, this might potentially explain things like dark energy or dark matter, those mysterious phenomena that seem to be causing the universe to expand faster and, like, holding galaxies together even though we can't see what's doing it. Wild, right? So, how does David Lush get there? What's the paper's main approach? He shifts from the usual way physicists describe particle motion using so-called Planck equations to focusing on fully four-dimensional equations based on Minkowski space. Hang on, quick digression. Have you ever noticed how Minkowski makes it sound like we're talking spy novels or something? Honestly, someday someone needs to write Minkowski, space-time, detective. Sorry, back to the science. The point is, Minkowski's four-dimensional equations treat time and space on the same footing, rather than splitting off time as kind of an afterthought. Anyway, by using these more covariant equations, David gets some results that clash dramatically with what we see in, say, particle accelerators on Minkowski space. Hang on. Quick digression. Have you ever noticed how Minkowski makes it sound like we're talking spy novels or something? Honestly, someday someone needs to write Minkowski, space-time, detective. Sorry, back to the science. The point is, Minkowski's four-dimensional equations treat time and space on the same footing, rather than splitting off time as kind of an afterthought. Anyway, by using these more covariant equations, David gets some results that clash dramatically with what we see in, say, particle accelerators or our old friend Einstein's relativity, for example. He says that instead of E mc2 for rest energy, it's actually half that. Similarly, instead of traditional formulas for total and kinetic energy, we get E g2 mc2 2 and kinetic energy as p2 nautium, even for relativistic cases, with p being the relativistic momentum. That means when particles go really, really fast, these formulas would lead to less energy, sometimes almost half as much being accounted for after a collision. Well, if that's true, why haven't particle accelerators blown up or at least produced a zillion more particles than we actually observe? David argues it's because what's actually conserved in these equations isn't energy per se, but something called the temporal component of 4 momentum. That's a mouthful, but it's basically a chunk of math that, according to this view, tracks with observations but isn't exactly the energy we're used to talking about. Okay, practically, what does all this mean for you and me? Honestly, most of us aren't smashing subatomic particles daily. Instead, the big questions come in when we're trying to understand the deeper universe. Are these strange ideas a possible reason for why energy appears to be missing in galaxy dynamics, or why cosmic expansion seems to be, well, on overdrive? Maybe. David suggests that energy non-conservation, if it happens, could feed into what we call dark energy. Similarly, matter and antimatter could behave differently under these formulas, maybe helping make sense of missing mass or dark matter. These are still open questions, though. Nobody's saying we should rewrite the textbooks tomorrow. Also, if the way we calculate energy in quantum mechanics is off by a factor of 2, that might affect things like how atomic spectra are explained, or how electron spin-orbit coupling works, a long-standing puzzle in physics. But let's be real, not everyone will be convinced. There are obvious reasons to doubt these alternative formulas. E Asar MC2 has worked really well in experiments for over a century. If we accept the new view, a bunch of other things would need reworking, and not everyone will agree that's justified. So, should you toss out what you learned in physics class? Nope. This is just a horizon-expanding thought experiment, but it's worthwhile. If you're curious about how laws of nature are built and why some things are taken as absolute, David's paper is a reminder that sometimes competing views are out there, and that as scientists, we need to keep poking at the foundations. Science is a journey, not a final destination. Thanks for joining me today. Remember, you can check out the full paper by David Lush if you want to see all the details and equations for yourself, because, well, some things really need to be seen with your own eyes. And as always, this is just one perspective. Don't take my word for it or anyone else's. Let yourself be curious. Until next time, I'm Richard Price, and this was In Depth with Academia. Stay curious, and I'll see you soon.